Hi, Physics 2. This is Mr. Janowski. This is homework 4 from chapter 32, and this is problem 4, and this might be a bit of a doozy. So what are we doing here? Consider the arrangement of three charges, Q1, Q2, and Q3, shown to the right. What would be the net electric field at point 4? So point 4 is right here. There's point 4. Give your answer in unit vector notation. So let's start with step, always a good place to start. What are we looking for? We're looking for the electric field at 0.4, it's going to be the sum of the electric fields. So I wrote it as sigma E, more like a sigma. That's a sigma. Sigma E is equal to, and we have to give it in unit vector notation. So it's going to be question mark I hat plus question mark J hat, and the units for electric field are newtons per coulomb. All right, so how do we get to this thing? What we need to do, how do we get sigma E? Well, remember sigma E, another terrible sigma, is the sum of the electric fields due to the first charge, so call it E sub 1, plus the second charge, E sub 2, plus the third charge, E sub 3. So I've got to find these three things and add them like vectors. So I'm going to find them, express them in unit vector notation, and then add them together like vectors. So we might as well start with the first one. The first one is going to end up being the hardest one. 2 and 3 are not going to be that hard, but the first one's going to be the hardest one because this one is not directly to the left or right, and it's not directly above or below. It's one of these guys at an angle. So let's start with this. I need to know this distance here. So let's call this distance D1, 4, the distance from 1 to 4. So what I have is a sloppily drawn, I have a right triangle like this. All right, and I know two of the sides if I check these numbers. So x1 is 0, that's 0.7 meters. Okay, so this side is 0.7 meters. This side here, okay, y3 was 0, y4 is 0.4. So this side is 0.4 meters. Okay, so let's do some Pythagoras. A squared plus b squared equals c squared. So 0.700 meters squared plus 0.400 meters squared is equal to, c squared is really d14 squared. So if I do this in my calculator, 0.7x squared plus 0.4x squared. Oh, somehow I made a syntax error. There we go. Okay, so the left side of this ends up being 0.65 meters squared is equal to d14 squared. But of course, I don't want d14 squared. I want d14. So we'll take the square root of that. So d14 ends up being 0.806. I'll keep another couple digits. 2.257. I'll leave it there. So that many meters. So that is what that distance is. All right, great. I have that distance. I also want to know this angle. I just know in advance I'm going to need to know this angle, theta, in here. So how can I get this? If I'm looking at my right triangle, I'll switch colors to make this a little easier. So, boop. Do that. This angle here, theta. Okay, clearly this is H. This is going to be A. That's my adjacent side. And this is my opposite. So at this point, I know opposite and adjacent without any rounding. There is some rounding in H, so I'm going to avoid that one. I know opposite and adjacent, and I want to figure out theta. So which trig function does opposite, adjacent, and theta? That would be tangent. So remember TOA. Tangent of theta is equal to opposite over adjacent. Therefore, inverse tangent of opposite over adjacent is equal to theta. So I want to ask my calculator, what is the inverse tangent? Write that correctly. Inverse tangent of 0.4 meters divided by 0.7 meters. And that will be theta. And if you do that, theta ends up being 29.74. 29.74 degrees. So that's angle there. I'm sorry, that's the angle right in there. Notice 29.74 is less than 45, and my angle looks like it's less than 45, so I'm happy about that. 29.74 degrees. Yeah, that makes sense. So that's a good check that I've done my trig correctly. All right, so now I need to figure out the magnitude of the electric field at point 4 due to point 1. So remember our formula for electric field. The electric field from a point charge, let's see if I can squeeze this all in here. So E1, I'll lose the vector hat, I don't really need it for this part, is equal to K Q1 over the distance from 1 to 4 squared. Okay, so E is equal to K, I've got it down here at the bottom, 8.988 times 10 to the 9th. Q1 is 5.50 microcoulombs. 5.50 times 10 to the minus 6 coulombs. So with the charge, I write the unit. I almost always leave the unit off when I'm writing K because those units are annoying. Divided by D14 squared. Okay, now notice I actually already know what D14 squared is. It's this number. You can put that number. You know what? To be clearer, I'm going to do it the old-fashioned way. I'm going to write what D14 is. 0.8062 meters, and then square it. It'll end up being the same. Okay, so now we have this. 8.988 e to the 9 times 5.50 e minus 6 divided by 0.8062 x squared. If I do all that, I get E. So again, this is E1. I should have the subscripts. So the electric field due to the first charge ends up being 76057.1, et cetera, newtons per coulomb. So that's how big the electric field due to charge 1 is. Now let's do a little bit more thinking than that. So this electric field from 1, okay, which is a positive charge, which means the field lines are going to point out. Okay, so the electric field due to that charge at this point is going to be going out in this direction. So I can think of it like that. E1 is out here. What's this angle here? Okay, well, we have alternate interior angles. So this is going to be, theta is 29.74 degrees. See, there was a reason why they taught you that in geometry. Alternate interior angles with parallel lines and things like that. So we have that. So really what we need to do now is a step 0. So this is going to be step 0 for E1. I wish I had more colors. Step 0 for E1. So again, E1 is going to take the longest because this is the one that's at the angle. The other ones won't be that bad. So E1 is something like this. E1, and that is equal to, I'm going to keep all these numbers, 0.57 newtons per coulomb. What I want to know is, terrible E, E1x and E1y. So I need these components. And this is a right angle. And this is 29.74 degrees. So notice I'm keeping like extra sig figs, it's a good idea sometimes to keep extra sig figs in the middle so that you don't end up rounding too much. So I've got to do the trig. It doesn't matter which one I get first. Let me start with E1x. Okay, so if I'm looking at this triangle, this is H, this is A, this is O. So which trig thing does A and H? That would be cosine. So cosine of theta is A over H, and A is E1x over E1. This number divided by this number. Okay, so trust me with the math. What that's going to get me to is E1x is equal to E1 times cosine of theta. And hopefully I can squeeze in all of E1 on this one board. We'll see. So that is equal to E1, again, is 76057 newtons per coulomb times cosine of 29.74 degrees, which means E1x is going to be equal to 66039. The units are newtons per coulomb. And what does that really mean? Okay, so it's 66039. Notice it's going to the right. So I'm going to write this as 66039 I hat newtons per coulomb. So now I have that component there. Let's see what's going on. Now we need, is this going to be legible? I'll do it in green again. Now we need the y component. So yes, believe me that E1y is going to be E1 times sine of theta. So I'm saying basic trig argument, but I'm not going to do the whole thing again. And to save space, what's that going to be equal to? E1 is equal to 76057 newtons per coulomb times the sine of 29.74 degrees. Write it like that. So what does that get me? 76057. Whoop. 76057. I made a typo. Times sine 29.74. And I get 37729. So that means E1y is 37729 newtons per coulomb. And which way is that going? Notice that is going up, which means in I hats and j hats, in unit vector notation, that component is equal to 37729 j hat newtons per coulomb. So we've got that. If I were to combine that, I now have the two components in I hat and j hat. So what would the total for this be? I wish there were a purple marker. Purple would be a nice marker to have on this. All right, maybe Google will fix it eventually. Anyhow, if I do all of that, E1 will end up being 66039 I hat plus 37729 j hat. And the units for all this, newtons per coulomb. And let me try to circle that. Hopefully I don't write over it. Okay, I have circled that. So now I have the electric field due to charge 1 in unit vector notation. If you're watching this video and struggling on that part, this may be a good time to stop watching the video, because this was the hard part. Getting the electric field from Q2 is not going to be that hard. You don't have to do the step 0 and all this stuff. The electric field from Q2, okay, it is a positive charge. It's going to be something pushing straight to the right. So that one's component will be all I hat. From Q3, it's a negative charge. So this one's electric field will be pulling straight down at this point. So that one will be a negative J hat. And then when you add them, you just line them all up. So that's what you do. So again, at this point, if you were struggling, it was likely on this part, getting the all of the electric field from E1. I will continue the video and do the other ones and then just put it all together. But I imagine if people are having trouble, this was probably where they were having trouble. So anyhow, let's continue. We'll go to another board and we'll do E2. E2 and E3 shouldn't take that long. So what are we starting with? The electric field from E2 is going to be K, Q2, I like using subscripts for this, divided by the distance from 2 to 4. Again, we want this distance squared. So that is 8.988 times 10 to the 9th with all the other units. Q2 is 4.50 times 10 to the minus 6 coulombs, because it's microcoulombs, divided by this distance there is 0.700 meters. And that number gets squared. So that's a 2. Okay, so this gives us E2, 8.988 EE9 times 4.50 EE minus 6 divided by 0.700 x squared. And this component ends up being 82524.8. So 82543 is what I should really write. Again, I'm keeping more sig figs than I need. And this is newtons per coulomb. Now, if I were being more careful with my notation, which I guess I should be, what I should be writing is this. This is the magnitude of E2. And when I want to figure out, express it in vector terms, I should really be writing it like this. So E2 with a hat is equal to, okay, let's figure this out. Q2 is positive, so it's pushing the electric field out, which means the electric field at this point 4 is going to be going out this way. So E2. That's to the right, so that's positive I hat. So really what this is 82543 I hat newtons per coulomb. And that's an important one, so I'll keep that. On to E3. So E3 is going to be equal to K times Q3 divided by distance 3, 4 squared. So 8.988 times 10 to the 9th. Q3 is this. Okay. So I'll do it the negative way, and we'll see how we handle the math from there. Minus 2.50 times 10, that's a 10, to the minus 6 coulombs, divided by, okay, what is this distance here? That is 0.4 meters. All right, so if we do all of that, what do we get? We get E3 is equal to 8.988 EE9 times minus 2.50 EE minus 6 divided by 0.4 x squared. Okay, so what we have at this point is minus 140,437.5, call it 38. And this is newtons per coulomb. Put the comma in to make the counting a little bit easier. All right, well, let's do, so I've got a negative number. That's going to be confusing. What the hell is going on with this thing? Let's do this trick again. I put absolute value signs around everything. And then this ends up being equal to the positive version of that number. So I'm taking the magnitude of that electric field. So I've got that. All right, now let's think, what is this in unit vector notation? What is this in I hats and j hats? Q3 is negative. So the electric field lines will be going into it. So if I drew a bunch of electric field lines, they would all be pointing. Yep, as straight as I can draw them. They would all be pointing there. So what that means is the electric field up here at point 4, because Q3 is kind of pulling the electric field lines into it, the electric field line here is going down. So that means this contribution here, E3, is going down. That's in the negative j hat direction. So what we're going to write is that way. E3 is equal to, it's negative j hat something, minus 140,438 j hat newtons per coulomb. So now I have all three of the pieces. I've got all three of the electric fields due to the three separate charges. But again, remember what we're looking for is we need to add them all together. So what I need to do, just to remind you, is this. Sigma E at 0.4, I'll give it a 4 there, is equal to the electric field due to the first one, plus the electric field due to the second one, plus the electric field due to the third one. And these are all in unit vector notation. And the way you add things in unit vector notation is you just add them up. So really, I should have written it this way. Sigma E4 is equal to E1 plus E2 plus E3, and they would come down here like this. So what is E1? Remember, E1 is what we have over here. This was the long one. So 66039 I hat, 66039 I hat, and what was the j hat part? Plus 37729 j hat, 37729. And yeah, these are all newtons per coulomb. E2, okay, that's this number here. This one is all I hat. So this is 82543 I hat. All right, look, plus 0 j hat, but I don't really need to write that. So I'm just going to leave that out. Newtons per coulomb. And then E3. What is E3? E3 is minus 140,438 j hat. So this guy has no I hat component. So you could write 0 I hat. Really, you don't have to. It only has a minus j hat. Minus 140,438 j hat newtons per coulomb. So remember, the next thing you're going to do is add up all of your I hat terms and add up all of your j hat terms, and you keep them separate, and you see what you get. So, asking calculator, 66039 plus 82543 means I have 148,582 I hat, and then for the j hat side, 37729 minus 140,438, and I get a minus 102,709 newtons per coulomb. So this is what the sum of these four guys are. So I kept lots and lots of sig figs there. If I round this off, I'm going to get the answer up here. Technically, I kept 4 sig figs up here. Yeah, I get a little sloppy with the sig figs, but let me just rewrite it that way. If we kept 4, technically we're only entitled to 3 at this point. But if we kept 4, we would have 148, 582 is going to round up to 600. And if we kept 4 over here, I should put the comma in, we're going to have minus 102, comma 700 J hat, newtons per coulomb. So put a box around it. Does this match what we were looking for? It does. Yeah, we have the sum of the electric field. We'll go back to step, So yeah, this is what we were looking for. Sigma E. We wanted it in unit vector notation, in units of newtons per coulomb. And that's what we have. So we're happy about that. We give it a check. So yeah, long problem. Especially the longest part of this, the longest single part of this was getting this one. Getting the components for E1, because you have to do Pythagoras to get this distance here. Then after you did that, you did Faraday's idea, your definition of electric field from a point charge. Then you had to do a step 0 to get the components. And then from that, a good step 0, it makes it not too bad to get the components. We got this. Getting the other pieces, this one and this one weren't as bad. But yeah, lots of little places to make mistakes. So I feel like this video is probably getting really, really long. So I hope you found it helpful.